All right, so just like in the translational world, we also have a player of motion in the rotational world that allows me to get faster or get slower. So as this object is moving around the circle with a certain tangential velocity at that point, what if I start spinning it and it goes faster? Or what if I slow it down and it gradually gets slower because I have a dampening effect in the turntable? Well, we called that in the translational world acceleration. And just like in that translational world, we also have an acceleration in the rotational world. And we call that the angular acceleration. And it is very similar to the translational world. Remember, in the translational world, we said the angular acceleration, in the linear world, we said the acceleration was equal to our change in velocity per time. Well, our angular acceleration, we're going to use the variable alpha. Our angular acceleration is equal to our change in angular velocity over time. And so similar to that angular translational acceleration, we follow that same parallel. So remember, this is omega final minus omega initial over time. So that's our definition of angular acceleration. Now, if I want to go from, I could also talk about the translational acceleration. We've had these parallels in rotation to translation. And similar to what we've observed through looking at how far and how fast, our tangential acceleration can be given as our angular acceleration times the radius. However, we are going to look at cases of constant acceleration in all these situations. So we can utilize these relationships as we move through our discussion of rotational kinematics. Now, we've discussed our players. The next thing that we want to recognize is the power of relationships among these players and how we can use them to describe how an object's motion looks through time. And so let's rearrange this equation and see if we can give some rise to what that might look like and how we can make parallels to the translational stuff we know so well. I'm just going to rearrange this equation by bringing over my time and then adding omega initial. And when I do that, I end up with an equation that tells me omega final is equal to omega initial plus the angular acceleration alpha times time. Well, that should look familiar. Because remember, when we talked about translational motion, we said that V final was equal to V initial plus acceleration times time. In order to know what velocity I end up with, I need to know my initial velocity. And I need to know, we called this how much velocity we acquire, either going in a bigger number or getting in a smaller number, so acquires in quotes, over the time that the motion happens, the time of motion I'm interested. So similarly, in the rotational world, we have how fast I'm going rotationally has to be related to how fast I started plus how much rotational velocity I'm acquiring. Well, this wasn't the only player of equation of motion that we found powerful. We had another one. And that one also can translate. Remember, we said, well, if I want to know my final position, I'm interested, I need to know what my initial position is. I need to know my initial velocity because that's going to influence how fast I go instantly. And my acceleration plays a role. Well, I can parallel this equation in the rotational world too, such that my final angle, where I end up angularly, is equal to where I started angularly, plus how fast I started out, my angular velocity, plus 1/2 my angular acceleration times time. It's an exact parallel, and we can use that to describe the motion of an object that's rotating. and how that object changes its angular displacement. We often will manipulate this equation a bit more in the angular world, and we'll look at the change in rotation. How much angular displacement do we get? So simply subtracting the initial angle value, which we often just describe as 0, and recognizing that is within the displacement relationship. All right, so that's an equation that we've used. And there was one more, which combines these two ideas and gets rid of the time situation. And that was that our final angular velocity squared is equal to our initial angular velocity squared plus 2 alpha times our angular displacement. So these three equations of motion that look strikingly familiar to our equations of motion for constant acceleration in the translational world can also be used for constant acceleration in the rotational world. And so we'll use these equations to solve for ideas about how long does it take for an object to slow down when it's rotating, or how many rotations does it complete in a given amount of time, given an angular acceleration it might have, a slowing or speeding up, or whatever problem we are interested in looking at from a rotational standpoint. All right, good job.